Hello and welcome to lecture number 2. So in the last lecture we realized that to make a colloidal state we need two phases or two mediums. One we call the dispersion medium and another is called the dispersed medium. So today we are going to classify the colloidal materials in terms of dispersed and dispersion medium. So I told you last time that there is 9 possibilities. So let's take a look at this. So on here, on the top, I'm writing the dispersed medium, and this dispersed medium can be of 3 types, or rather, there could be 3 phases of the dispersed medium. So I'm going to write the names of the phases here. So here I go. The first is gas, and then I have liquid, and lastly I have here solid. So that means gaseous, liquid and solid dispersed medium. So likewise in this side also I can write the dispersion medium. And this dispersion medium would also have 3 phases. So gas, liquid, and here also we have solid. Okay, so therefore we have a 3x3 matrix basically. So we have a table, and so our next job is to identify these each different class of colloidal state or colloidal material. Okay, so let's start with gas and gas. So the dispersed medium is gas and the dispersion medium is gas. So well, any gas is completely miscible with other gas. So we have here a perfect solution. Okay, and in fact when both the dispersed and dispersion mediums are gaseous, we cannot form a colloid phase, a colloidal state. So one was taken out of those 9, so we have 8 colloidal states. So now let's move on to the next one. Liquid is the dispersed medium and gas is the dispersion medium. So that means what? We can think about liquid droplets in air. Okay, so what is the type, what is this type of dispersion medium called? So this is called liquid aerosol. Okay, so that means small liquid droplets. The examples are actually fog, mist, etc. Okay, and also we actually take perfumes or deodorants. So the application medium is also a colloidal phase. That means small liquid droplets of organic molecules suspended in air. So next we have solid gas. So solid dispersed medium, dispersed in gaseous medium. So it is called basically aerosol. So this is actually solid droplets floating in the air. Okay, and examples are we have these dust particle. So any pollutant you see floating in the air, these are the examples of the aerosol. That means solid dispersed phase in gaseous dispersion medium. So also some other examples could be smoke, and another example is cloud also. Okay, and then we move on to gaseous dispersed medium and liquid dispersion medium. Okay, so this type of colloidal phase is called foam. So that means we can think about the aerated water. Okay, so what would be the example of this? The example of this, there are many. So we can think about food item, whipped cream. This is one foam. Or we can think about toiletries like shaving foam. Okay, so these are all examples of foam type of colloidal phase where gas molecules are dispersed in liquid. Then we next move on to a very important class of colloids, very interesting, and we have to learn a significant amount of this during our course. This is liquid dispersed medium and liquid dispersion medium. So liquid in liquid, if they are completely miscible, then again we have a perfect solution. We will not get a colloidal phase. But there are many liquids which do not mix with each other. And this type of colloidal phase is called an emulsion. So there are many applications of emulsion, and therefore there are many examples of such emulsions. So examples, if we think about food, the first thing that comes to our mind is milk. Milk is an emulsion. Okay, and I will later tell you what is the milk composed of. And then another thing is called mayonnaise. You must have heard about this. This is also a food item, and again, it's a type of emulsion. And also paint. Okay, the industrial paint that we use to cover or coat the surface of the walls. This is also an example of emulsion. Okay. Then we come to solid in liquid. Okay. So solid in liquid is simply called sol. And this is our most known type of colloidal phase. So any solid particles suspended in liquid. Okay. So remember, there is one term though. This is related with the sol. This is called hydrosol. Okay. So the hydrosol is the class of colloids when the dispersion medium is water. Okay. So H2O, if taken as the dispersion medium, then it's called the hydrosol. So, but this is basically a sol. So examples of sols are many. We can think about tea, coffee, because it is made in water. So water is the dispersion medium, so it's a hydrosol. And also we can think about gold colloids. So colloidal gold particles dispersed in water. It could be nanoparticles, could be microparticles, are also examples of this sol. So in fact, lots of materials when produced as microparticles, crystals or nanoparticles, nanocrystals, when we suspend them in liquid, maybe organic solvent or water, they all form, if they form a stable colloid, and we call it a sol. Okay. And then we have gas in solid. So gas molecules dispersed in solid medium, it's called solid foam. Okay. So yeah, this is it. It might be a little hard to imagine that gas molecule is dispersed in solid, but yes, it happens. And there are a few classes of materials known as the solid foam. And one thing we can easily think about that is the styrofoam. Okay, so this is a material, light material. You have heard about it. So it's a kind of a polymer, and so gas molecules are dispersed in those solid polymer. So it is called the styrofoam. And another example is a type of stone known as a pin stone. Okay, and there are other materials also. So expanded polystyrene also, and this also has a name. So okay, so another class of material, it is known as aerogel, is also this type of colloid. So gas molecules dispersed in solid. Okay, so aerogel is a type of material. So as we go along, we will learn a little bit about these aerogels. Okay, so our next example is liquid in solid. Okay, so liquid in solid, it is also sometimes known as gel or solid emulsion, or also known as solid emulsion. So liquid phase dispersed in solid, and examples. Well, there are many examples in food industry, because we come across, we consume many foods in terms of gel or jelly type of thing. So examples are plenty. We can think about few like jelly, okay, and there are other things like fruit jelly or fruit jam is also this kind of gel or solid emulsion. Then there is a thing called agar, okay, and there are naturally occurring substances, opal or pearl also. Is liquid dispersed in solid. So these are naturally occurring items. And also these another thing is called gelatin, or rather moist gelatin is also comes under this category, that is gel or solid emulsion. So at this point I would like to tell about these two things a little bit, jelly and gelatin. So jelly is a food item that we normally consume by spreading on bread and other baked items. So jelly is nothing but the fruit extract. So here the fruit extract is liquid fruit extract. It is dispersed in a solid polysaccharide known as pectin, which is derived from plants, and that basically makes it jelly. Okay. And then I told you there is another part, gelatin. Okay, so this is a little bit interesting because when you take gelatin usually extract as a solid form. So when you moist it, that means when you take water in this solid gelatin, it gives you a jelly or gel type of appearance. It becomes transparent also. This is called gelatin. Okay. So what is gelatin? So gelatin is a type of class of a mixture of proteins and peptides derived from the partial hydrolysis of animal skin. So some extracts from animal skin undergoes partial hydrolysis to form gelatin. So the moist gelatin is easily found in many fruit many food item, even in medicines and other commercially available items. So one of the most common thing where you will find gelatin, you think about gummy candies. Have you heard about it? I think you must have tasted it. So all the gummy candies, its significant portion contains gelatin. So now I told you this is proteins and peptides derived from animal skin. So this is basically animal protein. So those gummy candies are actually it's not a vegetarian item from any angle. Okay, so so from this knowledge, I hope that will be clear to you. So anyway, there are lots of examples. I'm not going through all this. Last we come to solid in solid. Okay, so this solid in solid is known as solid sol or solid suspension. Solid sol or solid suspension. And you can think of, we can tell me that even it's a kind of an alloy, okay, but actually it is a bit different from the alloys, because in alloy we have a homogeneous mixture, but here actually some solid particles are suspended in another solid phase, okay, so that's why it's a little bit different than alloys. So there are two examples at this moment I can think about. One is pigmented pigmented plastics. Okay, some solid polymers, pigmented particles are dispersed in plastic, so that's how you get pigmented plastics. And there is another example. It's called cranberry glass. So also it's known as tainted glass. Uh, if you go to Europe, in the churches made in the medieval ages, you will notice there are some tainted colorful glass. So the origin of the glass is actually there are certain particles, could be the gold nanoparticles suspended in glass, solid glass. So those kind of glass forms colloidal phase, and it's nothing but a solid sol or solid suspension. So there are few special types of examples and there are common types of examples. So what we learned that by taking a combination of both dispersed and dispersion medium, we can form 8 different types of colloidal state. Okay, so I hope it is clear now. So now we move on to some general definitions of surface, interface, and the role of surface in the colloidal state. Okay, so I'm going to clean the board and I'm going to talk about the role of surface in colloidal science. Okay, so let's define interface and surface. So let's imagine that there are two phases. Here I'm writing phase 1 and here I'm writing phase 2. Now a boundary that separates the two phases is called the phase boundary. So any phase boundary can be regarded as an interface. Alright. Now if either any one of these phases, okay, so let's write if either of the phases is either air or vacuum, then that interface is called surface. So that's the only difference. So that means all surfaces are actually interface, but not all interfaces are surfaces. Okay, so I think with this things are a little bit clear. Now you see that colloids means dispersed medium and dispersion medium, and there will be a phase boundary. So for every colloids there exists an interface. It may be surface, but it may not be surface, but of course it is interface. So colloids and interfacial or colloidal science and interfacial science are two inseparable things. Alright. So next we will see that what is the role of the surface in colloids. Okay, so already we have understood the role of interface, but once again there is one special consideration that we must know when we talk about surface. Okay, so just imagine we have a sphere. Okay, so this is a sphere and it is a solid sphere. Okay, so solid sphere means outside it is air. Okay, so that means the outer area or the interface is actually a surface, because it is the sphere is interfacing air or vacuum. Okay, so now the solid sphere has a radius r is equal to 1 centimeter. Okay, so the question is the surface area A is pi r square, so that means 3.14 approximated centimeter square. So the area is 3.14 centimeter square, and the volume B should be 4 multiplied by pi, that is 3.14 divided by 3 r cubed. So r is 1, so centimeter cube. So this much is the volume. Okay. So now the question is, if we try to fit in the same volume, that means the volume is this much. So if I try to fill this much centimeter cube volume by some smaller spheres, so smaller spheres of 0.1 micron radius. Okay, so here r is equal to 1 centimeter. Now I want to fill this sphere with smaller particles by radius r is equal to 0.1 micron. So 0.1 micron essentially means 100 nanometer. Okay. So the question is, how many spheres we require to fill up this much volume with 100 nanometer smaller spheres? You can calculate, you will find a number. But if I ask you, what would be the surface area, total surface area of those many number of smaller spheres combined together? Now, if we do our math correctly, that area, that means A with r is equal to 0.1 micron spheres should be equal to something like 314,000 centimeter square. So can you imagine that? So here we have 3.14 centimeter square surface area of volume of sphere with 1 centimeter, that is filled up by sphere with 100 nanometer radius. The cumulative surface area of all those spheres would lead you to this much centimeter square. So that means here these dimension is strictly in the colloidal region, right? So this is a colloidal dimension, but this is not a colloidal dimension, this is bulk dimension. So it also tells us that whenever we talk about colloidal dimension, it is nothing but we are talking about a huge amount of surface area, or a significant proportion of colloidal material is surface. That means an open interface interacting with air or vacuum. All right. So with this calculation, we come into a conclusion that interfacial area or the surface area, or in other words, interface or surface, is a very important part in colloidal system, and we cannot separate each other out. So that's why whatever the subject we are talking about, it is always pronounced together, or named together, colloids and surfaces. So these are the complementary part to each other, and we are unable to separate. So now, talking about the surface, since colloidal molecules have high surface area, so there is also a problem associated with the colloidal materials due to having such high surface area. Okay, so it is called a problem of stability. Okay, so now we are going to discuss a little bit that why does that problem arises. So that means why it is not always advantageous to have a very high surface area, and why sustaining a high surface area is a great deal of problem, challenge in colloidal materials. Okay, so that means it is not easy to form a colloidal phase because of the problem associated with high surface area. Why is that? I'm going to clean the board and I will explain you right away. So now let's take a look at the hypothetical situation for a material. Okay. So suppose we have a material here. It may be solid or liquid, whatever. Um, uh, so okay, let's call it a substance, maybe solid substance or liquid substance. So means non-gaseous substance. So uh, this is the surface interfacing air, and this side is our molecules are there. So as we go towards bottom, there is the bulkhead, and we move towards this line. That means we are going towards the surface. So let's think about any molecule here near to the bulk. Okay, so we call it B because it's a molecule staying at the bulk. So this molecule would be facing intermolecular attractive force by the molecules that are surrounding this molecule. And this intermolecular attraction force can be felt all around 360-degree solid angle. So with this kind of arrow, I wanted to mean that this molecule at the bulk is feeling the force of attraction in all possible direction, because there are other bulk molecules. So I am not drawing all the bulk molecules, but this is just a graphical representation. So like this bulk molecule here is facing or experiencing the force of attraction in all direction. Okay. So that means there is no driving force that present for the molecule, bulk molecule, because the net force means that there is no force in the net direction. Okay. But think about the molecules that are coming towards the surface, okay, or present near the surface. So near the surface means let me draw this kind of molecule or something like this. Okay, this is just right near to the surface. So there you will see that once again it will experience this force of attraction towards the bulk, because the molecule at the bottom would be bottom or side would be pulling the molecule towards the bulk. But you see, there will be a significant portion from here to here, from here to here. So these are called the surface molecules. So the surface molecules would not feel any force of attraction towards the air phase. So that means the molecules present at the surface, all the molecules that are present at the surface like this, would be experiencing a net force of attraction towards the bulk. So that means what? So that means if this material is a fluid, means think about if it is a liquid, so the surface of the liquid will always feel a tension towards the bulk. So the surface would like to contract, and the energy due to which this happens, we call it the surface energy. And the surface energy has also another name, surface tension. Okay. So the definition of surface tension is a bit different due to some technical reason, but the origin of surface tension is due to surface energy. So any materials, be it solid or liquid, because for liquid surface energy is more conspicuous, but solid it is not that much, but the surface energy is always associated. So the origin of surface energy is due to the unneutralized force of the intermolecular attraction coming from the bulk. Okay, so the more is the surface area, and now that's very important. More is the surface area, more is the surface energy. Okay, so this is very important because the energy is also proportional to the area. Obviously, if we have more unbalanced molecule at the surface, it will experience more force towards the bulk and the surface energy is more. So, if I have taken a larger sphere and break it down into smaller sphere, that means I am increasing its surface energy, surface area. That means I am automatically increasing its surface energy. So that means the surface would be unstable, simply. So we have to have another neutralizing force, another stabilizing force to make those materials stay in this high surface area condition. Okay, so therefore we have to say that to make a stable colloid, colloid means we are talking about the colloidal size regime, so that means already particles are in certain size range from nanometer to micrometer, where expected, I have shown you, it is associated with high surface area, means high surface energy. To make a stable colloid, we need to take care of the higher surface energy. Okay, so that means we have to stabilize the surface, as simple as that, so that the surface becomes comfortable and so that the material can stay in the colloidal phase. So another aspect is the nanoparticles. So why is it so why it is difficult to make nanoparticles or form a nano-sized dimension of any material? Because nothing but the fundamental reason comes from the surface energy. See, colloidal materials are majority micron scale, but if we think about the nanoparticles, these are also colloidal particles. If its size, say, falls below 50 nanometers or 10 nanometers, so can you imagine what's the huge amount of surface area it has, and it is associated with what a huge amount of surface energy. So it is always a challenge for material chemists to form a stable nano-sized dispersion in a medium like water or other organic solvent. The challenge is to pacify the surface energy. That means you have to make a stable surface. Okay, so some surface chemistry is required to do that. So in the bottom line, we have an idea that okay, colloid is associated with surface, and surface is associated with surface energy, and in liquid it is expressed as surface tension. So in order to make a stable colloidal phase, we have to stabilize the surface, or surface needs to be taken care. The surface area or energy needs to be taken care. Okay, so now we have an idea. So now let's once again simply describe that why this colloidal phase or colloidal science is important for us. So you see that the colloidal materials or colloidal state actually it serves as a bridge between the molecular world and the macroscopic world. So molecules angstrom size, macroscopic world, okay, millimeter size, and beyond that. So the colloidal dimension actually is bridging between the two, and also it covers nanoscale materials also. Okay, so as you see, to encounter colloidal materials or to study the colloidal materials, one has to have the knowledges of chemistry, physics, okay, basic biology, because many biological entities are in the colloidal range like proteins, DNAs, virus, bacteria, biomolecules. So any colloidal material is ready to interact with those biological entities. And to make colloidal materials, you need a knowledge of chemistry to make them stabilized and to characterize those colloids. You need significant knowledge of physics and also technology because it covers the nanoscale materials. That means any knowledge of nanotechnology is basically based on the colloidal science. So the colloidal science is actually comprised of chemistry, physics, biology, and technology. So it is really a multidisciplinary field, and you cannot demarcate that this is physics and this is biology. So it's nothing like that. So, and also basically the material science also overall. Okay, so all these subjects are associated in this colloidal domain. Okay, so the colloidal and surface science is comprised of so many interdisciplinary fields, and it has a huge applications. Applications in nanotechnology, biotechnology, medicine, and in our daily life, like food items. Okay, and industrial, commercially helpful items, industrial materials like paints, like building material, construction materials, and the list is basically endless. And food industry is just invalid without a solid knowledge in colloidal science. So this is the importance of colloids, and we should be able to appreciate. That's why colloids and science is such a meaningful topic for us, and I believe everyone should have a very basic knowledge of these colloids and surfaces. So anyway, before we finish today's lecture, as an introduction, there are a few more topics that I will just mention, but it is your job to study those from the prescribed textbooks or for any other source, because those are very preliminary and I won't be covering in details, but probably in exam you may face questions from these little topics also. So I'm going to enlist a few of them over here. Okay. Okay, so there could be further finer classifications of colloids. So when we talk about dispersion medium, so that means a colloidal state where we can take the colloidal particle or salt particles in the liquid dispersion medium, and when the liquid is mainly water, then there could be few more classifications of colloids. So under that category, we can have such classifications. So somewhere you will find this in your textbook, hydrophilic colloids, and then we have hydrophobic colloids. So from their name, you can easily associate. Hydrophilic means the colloidal materials or colloidal salts that like to be suspended in water. Okay, and so that's why I said liquid dispersion medium. Hydrophobic, that means they tends to stay away from water, so they would love the organic solvents mainly, or non-polar medium. And then another category is called the association colloids. Okay, so this is nothing but a self-assembly known as micelle. And during our course, we would study great details about this class of colloidal phase called micelle. But this is a way, micelles are also made in basically water, polar medium. So this is the classification by taking consideration as a liquid dispersion medium. And also there are two more terminologies that is called coagulation, and there is another term called flocculation. So these are also very important terms routinely used in terms of colloidal dispersion. So our colloidal salt dispersing mainly aqueous medium. So from the textbook or from any other source, you please study these two words. Okay, means what are those? Maybe there you should be able to write simple small paragraphs, about 50 to 100 words about this coagulation and flocculation. What are those and what are their applications and advantages, etc. So on this note, I would like to mention the name of one great scientist. Okay, so probably I'm sure you have heard about it. His name is Michael Faraday. So his contribution in colloidal science will remain always immortal because he did some fundamental work on gold colloids. Okay, so in fact, Michael Faraday was the first one to show that the gold metal can be made in nano dimension or in in colloidal scale. Okay, so he first made a stable colloidal gold suspension. So he can be considered as one of the forefathers of this colloidal science. Okay, so with this I finish our introduction chapter, that is lecture 2. So from lecture 3 onwards, from next lecture, we will study the theories for the stability behind colloids. So in other words, that how colloidal particles remain stable in a liquid or mainly in water medium. So there had been a Nobel Prize winning theory. So it means so that is the stability of colloids is a very important subject, a complicated one, but we will learn it in a simple manner because it's already a Nobel Prize winning theory, as I mentioned. So you please study these video lectures carefully and take down notes wherever necessary, and you please go through your textbook. Stay put, stay safe, and I will see you in the next lecture. So till then, goodbye.